Assalamu alaikum students, welcome to my channel Physics with Hasnain. Today we will study entropy. It is an important concept in the theory of statistical mechanics or thermodynamics. We will see its definition and we will see why we study it, its mathematical form. These are two of them. One corresponds to statistical mechanics and one is in thermodynamics. We will see how we can define second law of thermodynamics in terms of change and entropy, and at last we will derive change and entropy for free expansion, or it is also called Joule expansion. First of all, we define entropy. This uh, is a measure of number of microstates of the system at AC it should be possible number of possible microstates of a system at specific temperature. It is a measure of number of possible microstates of a system at specific temperature. I want to here add something that you should have knowledge of classical mechanics, because here we are using some terms such as microstates and phase space, which are commonly used in classical mechanics, so you are not going to understand this lecture without having basic knowledge of classical mechanics. So, a microstate means a state of a system instantaneously. If we draw a phase space diagram here of some thermodynamical system, we know that a curve in phase space represents evolution of the system in time. Each point in this phase space diagram represents a state instantaneously. So each point in this phase space diagram is a microstate. More the length of this curve, more we have the possible number of microstates. I have written possible because every microstate or every point which can occur later in time, it will be included in the definition of entropy. So I have shown this phase space diagram only in one dimension. Actually, it is a six-dimensional phase space, x, y, and z, and there are three corresponding momentums p. So in general, we not measure its length, but we measure volume in phase space. So we generally can say more the volume in phase space, possible volume in phase space, which can the system have, more will be its entropy. Now next move to the in our next point, why we study it. Its answer is in the definition of entropy, because it tells us that the system has microstates. Microstates can be quantum states. When we have an entropy for a system, it simply means the system should have quantum states. We mainly study statistical mechanics for quantum mechanical systems of many particle theory. I want to add here one more thing, is that black holes also have entropy. Nowadays, many physicists are searching for its quantum states. It will be an it will be a great advancement if we could find quantum states of a black hole. Now next is our mathematical formula for entropy. There are two of them. One is statistical and one is thermodynamical formula. In statistical mechanics, we define entropy exactly. It is represented by S, and it is equal to Boltzmann constant times natural logarithm of omega, where omega represents number of microstates. Sure. So omega represents number of microstates. We have taken log in order to lower its value. Actually, omega is of order of 10 raised to power 23 or more. So we have taken log in order to lower its value, and Boltzmann constant is necessary because natural logarithm has no dimension. Boltzmann constant is necessary to include its dimension because it can only then is dimensionally equal to the definition of entropy in thermodynamics. In thermodynamics, we study entropy change as integral of it should be capital Q. Integral of dq over T, where Q is the heat transferred to a system at temperature T, and this integration is taken from volume first or volume final. Or generally we can uh, define point 1 because it can be a closed system where volume do not change. So I am only writing I and F for initial and final states. From this definition, we can see that entropy should have dimension of Joule per Kelvin, Joule for Q and Kelvin for temperature. Therefore, to match the dimension, we have included Kv, where Kv has a dimension of Joule per Kelvin. Entropy is a state variable because it is not dependent on the path or the way in which it is changed. If we have a, for example, if we have a volume pressure diagram, it is volume, it is pressure. Pressure volume diagram, let the initial point or initial pressure and volume are P I and Vi. If we change its pressure or volume through mm, any way, either through heating it or by expanding it or including another number of particles, it can be changed to another pressure or volume by any means. And for example, if we change this to this volume Vf and this pressure Pf, there can be numerous paths between these two initial and final points. This can be either this path, this can be either this path, this can be either this path. From every path, the change in entropy depends only on the initial and final points. In other words, uh, change in entropy corresponds to every path is the same. So that is why a it is called a state variable. These two definitions of entropy are equivalent. I'm going to show their equivalence by an example here. Suppose we have a system of particles which are enclosed in a container and there is a piston above them. When we heat up a system, I mean give it to energy or heat delta Q, the piston rises above and the internal energy of the system increases. Entropy change for thermodynamical system can be written for constant temperature as delta Q divided by T, because when temperature is constant, it can be taken out of integration and we are left with change in heat. So this heat changes the internal energy of the system, and if for simplicity we keep its temperature specific constant, we are left with this formula. This is uh, valid for ice. This is valid for isothermal processes. So now entropy depends on three things. One is internal energy, one is volume, and this third one is number of particles. All these things change the number of states in our phase space diagram. How internal energy changes the number of states in phase space is that when we increase the internal energy of the system, some of particles may be excited to higher energy levels, thereby having more points corresponding to higher momentum in the phase space diagram. So increasing internal energy can lead to increase in number of states. and thereby increase in entropy. Volume is directly related to configuration space. Configuration space is the subspace of phase space. When we increase the volume, configuration space expands and therefore the entropy changes. Similarly, entropy can be changed by change in number of particles. We have argued before that phase space is six-dimensional, but for n number of particles it is more generally 6n-dimensional. I have said it before for simplicity that it is six-dimensional because I was not concerned about the number of particles. For one particle system it is six-dimensional, but for n particles it is six-n-dimensional. Therefore, when we increase the number of particles, entropy increases, and number dependence of entropy can also be understood by another example. That we have another example here. Let we have a particle in a box and it has three quantum states. We are considering a quantum example, and this particle can be in either of three states, E1, E2 or E3. There are three possible states, E1, E2 and E3. Let we have another system separated from this, and there is again one single particle in it, and similarly there are three possible states. One is E1, but this time I am labeling this by dash, E1 dash, E2 dash and E3 dash. So when we consider them separately, both of particles have only three possible states, E1 to E1, E2 and E3, and similarly for particle 2, this is particle 2 and this is particle 1. And particle 2 has three possible states, E1 dash, E2 dash and E3 dash. When I remove the barrier between them and combine them into one system, there are 9 possible states. How? Let me elaborate this point. Let's suppose the particle 1 is in state E1. So there can be three possible states for particle 2. E1 dash, particle 2 can be in either E1 dash or E2 dash or E3 dash. Similarly, if particle is in E2 dash, particle 1 is in E2. So there can be three possible states again for particle 2, and these are E1, E2 and E3 dash. E1, E2 dash and E. I am not writing for again E3. You should understand that there are total 9 possible states for the combined system. So when we increase the number of particles, entropy increases. And if we decrease the number of particles, entropy decreases. But total entropy of the system should increase, and we will see it in the second law of thermodynamics part. Next, entropy change can be written by chain rule as change in entropy equals partial S by partial U into delta U plus partial S by partial V into delta V and partial S by partial N into delta N. We can write this because S is a function of U, V and N. In this case, we are not going to discuss entropy dependence on time. I'm sorry, N, number of particles. We are considering a simple case where number of particles are same. So we are left with only two terms. Now it is known from statistical mechanics that partial S over partial U equals 1 over temperature, and similarly partial S over partial V equals pressure, where P is pressure divided by temperature. I am not going to derive these two relations, but these are known from statistical mechanics. And now I am going to put these two relationships in this equation, and I get delta S equals 1 over time delta U plus P divided by time delta V. Now I am going to put value of delta U by first law of thermodynamics, which is delta U equal to delta Q plus no, it is minus minus P delta V. So it will become 1 over, let's move T to another side. T is here, delta S and T, and we are only here with value of U, that is delta Q, minus P delta V plus, and this term is P delta V. Both of these terms cancel each other, so we are left with delta S equal to it should be delta. There is a difference between delta, this delta and this delta. This is big change, and while this is small change. Delta Q divided by time. So I have derived this expression from statistical definition of entropy or its dependence on U, V, and N. And this is equivalent to thermodynamical definition of entropy. Now our next point is to define second law of thermodynamics in terms of entropy. It can be defined as change in entropy should be non-negative. It can be equal to zero, but it cannot be negative. It can only positive or zero. That is why it is also called an indicator of time, because time change is also non-negative. We cannot go to past because in that situation time change would be negative. Entropy change only in the direction of time. So that is why it is an indicator of time. Now our next point is to derive entropy change for the Joule expansion. Joule expansion is a kind of expansion in which the system of particles is allowed to expand in vacuum. Suppose we have contained many particles in one container of volume V, and there is another volume of having no particles, and there is a vacuum in it. It is these are disconnected from each other. If we remove the blockage between them, particles would rush into the second container and will fill it. This kind of expansion is called Joule expansion. Let the initial phase space volume is omega I. After the expansion, it changes to 2 to the power n, where n is the number of particles. Phase space volume changes by 2n times the initial volume of the phase space. I will explain this point later, but let me derive the value of change in entropy first. This is the final volume of phase space, omega F. So final entropy using the formula is Kb equal to log of omega F, or using the logarithm property we can write it as Kb log of 2 power n plus kb log of omega I. One thing I have, okay, all right. This is initial entropy. So I can take it to another side of the equality and write the total as change in entropy. I can take this to another side and this is entropy final minus initial entropy, where these are I have written this directly, and on other side I can remove this power using log property as n k b into log of 2. This is the formula for change in the entropy in Joule expansion when volume is doubled. It is not arbitrary, it is a special case in which volume is doubled. Now I am going to show you why I have taken this 2n. Suppose we have a system of one particle here, which is in a container of volume V, and it is connected to another container of volume, same volume V. Initially, when the particle is enclosed in only one container, its configuration space volume is omega V. I am considering only configuration space. When it is allowed to go into another container and move in 2V volume, and is allowed to move in 2V volume, its configuration space doubles similarly as we have doubled the volume, because configuration space consists only on position variables, so it should double. If there is another particle here, now the total configuration space is, where V is for configuration and T is total. The total configuration space is 2 omega V for one particle multiplied by 2 omega V for another particle, because we have the similar argument we have given here. One particle's state corresponds to all other states of the particle. Here we have the similar case. Each particle state corresponds to all possible states of another particle. Therefore, we have multiplied both of them, and if there are n particles, the total configuration space is 2 power n omega v, because there will be n such brackets, and if the configuration space is 2 to the power n times the initial volume, we can write the total phase space as final. Final phase space is 2 to the power n times initial phase space volume. So that is why I have written this to here. I hope you have understood the lecture. If you have any question, you can ask it in comment section. Thank you.